Hi everybody! So let's learn about a new way to draw lines. So based on our previous video, this is attempt number 3, and spoiler alert, it's the one we're going to go with. And this is Bresenham's line algorithm. And it's actually really cool. A lot of people struggle with this algorithm, and I think the reason why is because a lot of the proofs online, or a lot of the textbook representations, they do two things that I don't like. One is they start from the most optimized form and expect you to pick up all the pieces. No way. Start from the intuitive form and then optimize until you see it's the same thing, right? The second problem that I see people do is they explain it really mathematically with complicated terms. I mean, if you're in advanced math and you know what that all means, that's great and all, but for the rest of us, we're just trying to draw lines, right? So I hope that this approach that I'm giving to explaining it helps keep it reasonable. Maybe simple is not quite the right way, but the intuition should be there, and you should be able to code it up and work through a few bugs, okay? So the first thing that this algorithm does is, instead of working on these equations in terms of the line and trying to determine my step size, it says, no, we're going to work at the pixel level. We're going to work at the pixel level. So I don't want any fractions of pixels. I don't want any different coordinate systems. We don't draw the lines anyway until we're at the raster. Keep everything in your funny coordinate system until the end, and when you finally change coordinate systems into my screen and I have 1,000 by 1,000 pixels or whatever, now let's just work on the pixel level. And what I want to do is I just move from the start pixel of the line, move from the start pixel to the finished pixel, and I color my pixels along the way. So then there's no holes, no skipping errors, no rounding errors, okay? No holes and no rounding errors. I'm going to just draw a straight line the best I can along the way, okay? So that's the first intuition. Let's forget these coordinate systems. No, pixels. It's all integers, integer pixels, okay? Now what I'm going to do is draw a raster. See if I can get the same size. 1, 2, 3, 4. I want 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's do this. I'm going to draw a raster here. All right, 1, 2, 3, 4, 5, 6. Perfect. Cool. So I'm going to draw a line from right down here to right up there. Now the first thing, and this is actually more nuanced than it needs to be, but we'll come back to that in another video. But I'm going to mark the center of the pixel, but in reality, we know the coordinates are actually at the corners of the pixel. Small detail, okay? But it does come up again later. So I want to draw this line, and you know what I'm going to do? I have a pencil. I'm just going to not erase my line. Let's try that again. So much for having a pencil. I'm going to draw a straight line. There we go. I drew my line. Yay! And actually, I want to erase the edge there. Yeah, I didn't want it to go over. Okay, so I have my line. Now, of course, these are pixels, and they have to be colored or not. So how does this work? I'm going to skip down a little bit and start writing out some pseudocode. Let's see how much room I need. 1, 2, 3, 4, 5, 6, 7, 8, 9 lines. Okay, I'll start down here. So first thing, I'll do some calculations. I'm going to put delta, that's an A, Jim, delta, I need to practice my Greek. Okay, delta x, right? The difference in x is just going to be x2 minus x1. So I figure out how much does it have to go this way, left to right. How much is this way? This is my delta x, okay? And then I'm going to calculate, I got to turn off that auto eraser. I got to calculate the delta y, which is going to be y2 minus y1, and that's this way. This is my delta y. No big deal. First thing I'll point out to you, though, because it's going to come up again later, and I'm going to write it in like a different color. Here, I'll note that delta x, The change in x is bigger than the delta y. It's going more across than it is going up. Keep that fact in the back of your mind. That's going to come up again. All right, so I have the delta x, delta y. Let's calculate my slope, which is rise over run. Oops. So delta x, over delta y, that's my rise over my run. I have a slope. Cool. So let's do a few things. I'm going to set some variables. X, that's an x, y equals my start position, sure, right? Which is x1, y1, right? I set those variables. Cool. All right. I think I need to zoom out a bit. I need more room so we can see this as I go. So what do we do? What's Bresenham's line algorithm? Well, it looks like this. First, like I said, we want to step through every pixel. So I'm going to go through the x's one at a time. So because I know that my delta x is bigger than my delta y, I'm going to go through this x, this x, this x. I'm going to go all the way across till the end, and I won't miss an x coordinate. Now, because my delta x is bigger than my delta y, I know that this means, here we go. This means only one y pixel per x coordinate. Guaranteed. X moves faster than y. So any x, I only have one y coordinate. Okay. So let's see if I can start to bring all of this together. So I'm going to go through all those x coordinates while x is less than x2. So I'm going to go from left to right across my x coordinates, okay? I'm going to put a pixel at x, y. Awesome. Let's make it green. Okay. So I'm starting start location. So x, y starts at the start location. I put a pixel there. Cool. Next thing I do, I move x right. All right. So x plus 1 in this case, I move to the right. Now I'm here. Okay, I don't know if you can see that yet. I'm there. Now what do we do with the y coordinate? So far so good, but if I don't change my y, I'm going to get pixels all the way across here. And that's clearly not what we want. So here's where the second piece of magic comes in with this algorithm. As we step x along, we accumulate error in the y direction. So what we say is, hey, how much is y off from where it should be? That should be a where. Let's try writing out a little neater. Okay, so how far is y off from where it should be? Okay, so if I step across here, I'll highlight in red here that the y, as shown by my green line, it keeps the y. Y is right. Y. It keeps getting bigger and bigger and bigger and bigger. The error gets worse and worse and worse. Okay, so what we want to do is watch that error and go, when it gets too big, let's just move the y closer. Okay, so the way that we do this is first I'm going to add a new variable here called error. Okay, and then what I do is when I move my x to the right, I add to my error. I go error, and this is going to seem random at first, but I'll explain it. Error plus equals my slope. Okay, well think of it for a second. What is slope? Okay, slope. Rise over run. Or, I just calculated delta y over delta x. Or, how much change in y for each one change in x? My slope literally means how much does y change when x changes by 1? That's literally what it means. So I just changed x by 1. I moved x to my right here. I moved x there. How much did y change? Add my slope to it. and then it'll tell me how much y should have changed. Now, because we're dealing with pixels and these are floating point numbers, it won't quite be, in this case you can see my error is, okay, it's about 0.4 of a pixel, let's say. So maybe we'll go, you know what? I'm okay if it's less than half a pixel. I'm going to say I'm close enough. I'm going to draw my pixel here. Okay? Because the error is so small. But then when the error gets bigger, like the next pixel, maybe then I'll care. So if I update my algorithm, if this error is bigger than a half pixel, and depending how much of a purist you are, bigger than or equal to half a pixel. So if my error that I've accumulated of where y is supposed to be is bigger than half a pixel, let's go on the other side of that error. So let's step through this. Oh yeah. Then move y up in this case, and then update my error. Well, we take away 1 from it because we moved a whole pixel. So, you know, we take away 1 because we moved a whole pixel. We take that out of our error. So in this case, what's going to happen is I move right here and stop erasing everything. Thank you. So I move to the right here and I consider this pixel. All right. I add my error to the y, and like you can see now here, my error is much bigger, maybe 0.8 or something. I don't know, I'm making this up, of course, but it's much bigger. So I'm going to go, you know, that error is too big. I'm not comfortable with that error. Let's instead increase our y too, and let's color that pixel. And let's update my error. So my center is now here, and look, I'm going to add 1 to my error. So now I'm going to be at 0.2. Okay? Subtract 1 from my error because I've moved a whole pixel. So now my error is really small again. Let's loop around. So I move to the right. I consider this pixel. Wow, my y error now is like, it's really small. Probably 0.2 the other way, I don't know. So I draw my x here and accumulate that error. I consider the next pixel. I move over here. Well, I accumulate that error again. Well, it's still probably only 0.5 or so, maybe 0.4 I should say. Good, I don't mind. I draw that pixel again. I move to the right. I consider here. I add up my error. That slope accumulation is getting much too big. This is like maybe 0.7. I'm making these numbers up. So I'm going to increase my y, color that pixel, add 1 to my error, and now I have a new error of 0.3. I move to the right again. I consider this pixel, and then so on and so forth. My error, in this case, my error looks to be bigger. Again, my raster, if you can't tell, isn't exactly straight. So the error looks a bit bigger, so we would color that pixel if the error is too big. But it accumulates, and because it's floating point, you will get sometimes these uneven patterns like 2, 3, 1, yeah, 2, and my raster's not perfect. But the intuition here, I hope, works for you. The intuition is, look, slope just means rise over run. I'm going to go through every x pixel, and along the way, I'm going to add up. How much was y supposed to have changed? 0.2? Okay, that's not very much, but I'll keep it. I'll accumulate this error. I move again. Now it's 0.4. Getting close. I move again. Now it's 0.6. I'm going to move my y up, add 1, and be minus 0.4. So you accumulate that error as you go along, and when it gets too far, you move your y as well. With this algorithm, you're guaranteed to hit every x pixel, and you're going to have no holes, and you're not duplicating any of your work. Now, the only thing I haven't mentioned so far is, what do we start error at? You can start it at 0, but it's actually more correct to set it at 0.5. And the reason we do that is because you're actually using these corner coordinates. So you're actually there, and you're supposed to be in the middle of the pixel. So we call the y is off by 0.5 to start. That's the standard way to do this algorithm. We'll come back to this in the next video, but you know what? If you started with 0, it wouldn't be that, wouldn't really be that big of a deal. Okay, so that's basically it. If you can pause and maybe rewatch this, if you can understand this, you've pretty much got this algorithm under wraps. If you understand that I go through every x and I point a pixel there, and then I accumulate that slope into my y. If it gets too big, then I draw a pixel. Okay, so that's really cool. Now, what's next? Okay, I'm going to draw a new diagram for you. We got a problem. Here's our problem. This case I just showed you, haha, I gave you a hint before. Delta y is, x is bigger than delta y. This case I showed you only works in this quadrant. Octant, actually. It only works in that octant because it only works for up and to the right. So that's annoying. So now we've solved one. We need 7 more to go. Yay. Okay. Let's go at it. This was A. I'm going to call this one case A. We've already solved case A. We can do it. Let's look at case B. So it turns out that case B is basically the same. A was delta x is bigger than delta y. And they're both positive. Okay. Case B is pretty much the same, except x is negative. So we still have that x is going more than the y. So B, we still have delta x is bigger than delta y. Again, absolute values here. I'm going to write that a little neater. We have B where delta x is still bigger than delta y. So that's good. The difference is x is negative. Okay, x is now negative. So delta x is negative. So that's what's different. So we could rewrite the whole code, but it turns out we just have to make some tweaks. So to make this work with our existing algorithm, we invert, that's times a minus 1, our delta x, okay? So we just go delta x equals delta x, oops, times minus 1, or just minus delta x, right? So we invert that just to keep the polarity of the slope, okay? To keep polarity of slope. So that the slope still stays positive. Yeah, I think I made my notes too wide. That's okay. No big deal. So we invert delta x to keep the polarity of the slope. And then what else we need to do is we need to move left instead of right. Okay? If we're going in this direction instead of in that direction, we have to go this way. Okay? So, yeah. So instead of moving x right, we just move to the left. And that's actually a really easy way to do that. We go x plus equals step instead of move x right. And so then move x, what's the wrong pen? Step x. Okay? So then we pre-calculate ahead of time. Hey, is x negative, delta x negative? Yeah, it is. Okay, well, let's fix that. And let's make our step negative, okay? So that we move in the opposite direction. So a couple of if statements, yes. A couple of if statements later, you can use the exact same code as long as you have some if statements up front. So make some, I'll put this in blue. So you make your changes up front. Use same code. Awesome. So that's solved. We've done. A and B are solved. Now let's look at another case. Let's look at C down here. Now, again, delta x is still bigger than delta y, so everything works. And now x is positive, but y, delta y is negative. So everything the same, but instead of x going up, right and y going up, x goes right and y goes down. So just like B, C can be fixed with a couple of if statements. It's the same, but y is negative. Okay, so then what we do is we invert delta y, right? So delta y equals negative delta y. And then again the same, we move down instead of up. We can do that with a couple of if statements, and if I go back to my algorithm here, instead of moving y up, we use a variable called step y, and then we go, hey, is delta x negative? All right, reverse that back. We can't do negatives, but let's change our y step to be negative. So when we add plus equals step, we go in the down direction. And then, so we make changes up front. We use the same code. Awesome. Cool. What case is left? So we did A, B, and C, and then D is down here. Now delta x and is still bigger than delta y, but delta x and delta y are both negative now. So D, we just do both of them. Okay, that's all that we have to do. We do both B and C. Cool. And then, where is it? Yeah, same code. So now we can solve these big cases here and these big cases here using just that short piece of snippet and a few if statements up front that let you figure out which octant you're in, and depending what octant you're in, you make some exceptions. Now, we're only half done. I'm going to handle these in one big chunk. Okay, I'm going to call this region E. What on earth? Now for region E, something has changed. We've always had delta x bigger than delta y. That's here, right? We always had x going more this way than y. In these regions, delta y is bigger than delta x. Okay, so instead of going one x pixel and maybe move the y, we need to change our whole algorithm sideways. Let's go through all the y coordinates and maybe move x. Okay, so it's the same thing, but everything is reversed. E. So we do the same as A to D, but x and y are reversed. Okay. Instead of stepping through x, we step through y. Okay, and instead of checking error on y, we check x. So you do the exact same code and you reverse the x and y's, and you invert the invert the slope, because it's not rise over run anymore. We have run over rise, which is kind of weird, but you can figure it out. So we do the same thing, and we've solved all the cases. So in cases A to B, we can actually just use one piece of code. I shouldn't probably do that for readability. We can just use this one piece of code for A to D. Now, for E, though, we do need a second loop. Typically, it's the way it's done, right? So you go if delta x is bigger than y, you do the first line, else you do the second set of code. Okay, so you do my algorithm here, and then you invert x and y here. I really should tidy that up. So that's Bresenham's line algorithm. There's two parts that I went through, right? The first was understanding this base case. That's the hard part, okay? I would focus, if you're lost, you're stuck, and you want to implement this, forget everything, draw a line that you know has these properties. It goes right and up. Draw that line. Draw so the rise is bigger than the run is bigger than the rise, right? Delta x is bigger. Solve that first, figure it out, and then start tacking on the other octants. Because if you can get the basic algorithm down pat here, then the other ones are just if statements that shuffle your variables, and then the run, when the delta y is bigger, you take the same loop, you copy paste it, and you can tweak your variables to make it work. So this is a really nice algorithm. It solves all those challenges we had, and as you can see here, the code is actually pretty short, which is always nice. Yeah, and it's actually quite fast. Okay, Now, the last thing I'll talk about is if you do look at what time are we? Well, it's getting pretty late. If you do look at this online, it'll probably look quite different. And the reason comes back to how I started this. Optimizations. Okay? So what we see here is a couple of problems. I'm going to bring the red pen. First of all, that's a floating point. And then this is a floating point. Okay? And this is a floating point comparison. Those are slow. And integers are faster. Now, as I'll show you, it's not as important as it was 15, 20 years ago when, wow, it was really important. But it's still the case that in general, integers are faster. And so what people have done is they've done really clever tweaks, like instead of m equals delta y over x, you multiply everything by delta x to get rid of the division, you put it through the equations, everything starts to look really strange and funky, but it does the same math under the hood. So if you look online, you're probably going to see those strange variations, which mathematically are the same. So to finish up now, I want to, I should probably write this out. I want to give a demo though. The standard form that you'll see online does not use floating points. Okay. It's rearranged to use integer math, which is faster. Okay. So let's see if I can get my demo up. I'm not going to show you the code because I think you can implement it yourself. All right. So I'm going to post this online, what I've done here. There's some tweaks to make processing faster, which I did, but I'll share that later. Forget that. But what I want to show here is I'm making 3 million lines. I'm making 3 million random lines, and then I'm going to do three things. I'm going to draw them using the algorithm I just showed you, the floating point algorithm, and I'm going to time how long it took to draw 3 million lines. Then I'm going to draw them again using the integer-only version of that same algorithm. Like I said, used to be really different, really important, not so much on modern hardware. We're getting pretty good at floating points. And in the third case, I'm going to ask my graphics card to do it for me. So to be clear, in the first two cases, the CPU is doing all the work and just getting the graphics card to modify the raster. All the line calculation is happening on the CPU. In this third case, we're just loading up the data into the graphics card and asking it to do it. All right, so let's see how fast this goes. 3 million random red lines. Bam. Okay, still working on those first 3 million. Okay, next 3 million. All right, and we're done. So let's take a look. So the floating point algorithm was 9.5 seconds for 3 million lines. The integer was 8.6, and our graphics card could do it in 0.98. So I'm going to pause here and do some math real quick. Okay, I'm back. I did the math, and let's go back to my iPad. So the floating point operation, I got 313,000 lines per second. The integer is 345,000 lines per second. You'd expect that difference to be bigger, like on a smartphone or on a system with less aggressive floating point hardware. And then the graphics card is 30.1 million lines, 30.1 million lines per second. A little faster. And this is an old graphics card, GeForce 970. What CPU do I have? Okay, so my CPU is an Intel i7 8700K. I'd be curious to see how that would work on an i3 or maybe a slightly older CPU. I'm very curious to see. Okay, so that's it. Line algorithms, nice and fast.